What I'd like to do at the start of this video is give you some examples of power series with various radii of convergence and talk a little bit about the behavior at the endpoint. So first example. So this power series that I talked about at the beginning of section 4.2, n factorial x to the n, you can show using the ratio test that this diverges for any x except x equals 0, because in that case you're adding just adding 0 for over and over and over. So this one has radius of convergence. R, I'll use big R for the radius convergence throughout. And conversely, this power series, which many of you have probably seen before, x to the n over n factorial, this has radius of convergence infinity. You can show using the ratio test that this converges no matter what finite value x is. I didn't want to use the ratio test or the root test to prove that radii of convergence exist, because they're sort of finicky, puzzling things, but they are really the best way to actually compute the radii of convergence. Then now let me give you 3 power series that all have the same radius of convergence. We've got the geometric series. We've got 1 over n as our coefficients, and then let's have 1 over n squared as our coefficients. And all 3 of these have radius of convergence 1. You can use the ratio test. We know from proposition 1.4.4 that says essentially the radius of convergence of the geometric series is 1. And you can prove without too much trouble that these other guys have radius of convergence 1. Ratio test will do it. And let's think about what happens at the points that are a distance r, a distance 1 from our base point, which is 0 in this case. So this one diverges at plus or minus 1. And that's because x to the n, 1 to the n is always 1, minus 1 to the n is 1 or negative 1. Neither of them are converging to 0, and that's a necessary, if not sufficient, condition for convergence of a series. Now here, if we take x equals 1, x to the n is 1 to the n is 1, so we get the harmonic series, so it diverges at 1. But then if we take x to be negative 1, that's the alternating harmonic series, is minus 1 plus a half minus a third plus a fourth minus a fifth plus a sixth. So that one converges at negative 1. And last example, you can show using the integral test that this one in fact converges at plus or minus 1. And since 1 over n squared is positive, if it converges at 1, then at minus 1 it's going to converge absolutely. So it is in fact if you've got positive coefficients and you converge at positive 1, you've got to converge at negative 1 as well. So we've seen that you can have radius convergence 0, infinity, or finite numbers. You can get any finite number you want if you think about it hard enough. And we've also seen that power series at the radius of convergence, they can diverge or converge on one side and diverge on the other. I'd like to remind you now of a definition from section 1.4. We say that this series, not a power series since it's from section 1.4, just an arbitrary series, and maybe I'll call the coefficients Bn instead of An. We say that that converges absolutely. If the series of absolute values converges. And then we had two useful propositions about absolute convergence. The first is that if a series converges absolutely, so if the absolute values converge, then the converging absolutely is stronger than converging. The alternating harmonic series is the obvious example, is the classic example of a series that converges but not absolutely, and conversely, anything that converges absolutely, at least in the real numbers, it has to converge. And then here is our second proposition. Suppose they're in the book in the other order. Is that if you're adding up positive things, so this thing converges if and only if this thing is bounded. The supremum of all the partial sums if that is finite. So you may recall all this. If you're adding up positive things or non-negative things, rather, either they converge or they go to infinity. And if you're bounded so they converge, then the series without absolute values converges. And now here is the result for absolute convergence of power series. So let's start with the power series. And let's say it has radius of convergence R. And then if x minus c is less than R, then our power series now, by definition of radius of convergence, we have that this converges, but we can do better than that. We can say it converges absolutely. The proof is very similar to the proof of the proposition in the last lecture. So since x minus c is less than R, then there is a y with x minus c is less than y minus c is also less than r, then by definition of radius of convergence, converges by definition of our radius of convergence. But then if this converges just as we saw last time, so series converges, therefore the terms go to zero, and if the terms go to zero, they're bounded. Eventually you're close to zero, and there's only finitely many of them before you get close to zero. So we've got that this is finite. Now what we're going to do is we're going to use the comparison test. So we're going to take an x minus c to the n. This is less than or equal to. We've got an an. Then I would really like a y minus c instead of an x minus c to the n. So I can use my bound, and then I multiply that by x minus c over y minus c. Then we can take our power, and then that first piece is at most m. And since y minus c is bigger than x minus c, which is non-negative, I'm pretty sure I'm not dividing by 0. And then this series it's a constant times a geometric series. This thing it's a constant times a geometric series, so it converges by proposition 1.4.4. So our absolute value series, an x minus c to the n, converges by our comparison test, which is theorem 1.4.7. Next, we're going to prove sort of a technical proposition, but we'll see it's going to end up being very useful for us. So this says if we got a power series, then here is another power series. You can write it in a couple of different ways, n times an times x minus c to the n minus 1. Then since you can throw out this n equals 0 term because the coefficient in that case is 0, or if you insist upon having it be a power series where, the power is the coefficient n, you can reindex, go from 0 to infinity, n plus 1, then a sub n plus 1, and then x minus c to the n. So this other power series written in any of these three ways, that is going to have the same radius of convergence. So let's prove this. So let's let R be the radius of convergence of the original series. And let's let, say, P be the radius of convergence of the new series. All right, now, so here's the easy direction. We're going to show that P is, that R is at least as much as P. So let's suppose x minus c is less than P. And then by the previous proposition, we have that our series converges absolutely. So I'll go ahead and write that like this. That the absolute values converge. And so I don't think this is actually proven explicitly anywhere in section 1.4, but you can show it's true pretty easily. If you've got a series that converges and you multiply each of the terms by the same constant, then it also then it still converges. So in this case, we're going to go ahead and multiply by x minus c. That converges. And then just the comparison test. Which is in section 1.4. This thing converges. So that means that the radius of, so that means that our series and x minus c to the n, that thing converges absolutely, but we just need it to converge. So that means that R is greater than x minus c, and this is true for any x minus c that's less than P, so that means that your radius of convergence of the original series has to be it's the radius of convergence of the new series, the one with the NaNs in it. Now let's go in the other directions. So let's suppose that x minus c is less than r. And this one's going to be a little bit tricky. We're going to use the fact that we're converging for a bigger number. So let's let y be such that x minus c is less than y minus c is less than r. This is the same trick we used to prove basically the first proposition in this section, which was that power series have radiuses of convergence, and also for our absolute convergence. Then we have that this series that our power series converges absolutely. So this thing with all the absolute values, that is going to just regular converge. And now let's write the other series that we care about. We'll go ahead and take absolute values. That's the sum from, actually, let's go from 1 to infinity. And let's note it, and I'm going to go ahead and point out that this series is also going to converge if we start at 1. Whether it converges or not, throwing away one term doesn't stop it from converging. So this series, that's the sum of the thing we've got before, an y minus c to the n, and then we multiply that by n times x minus c to the n minus 1 over y minus c to the n. So now it's just this leftover piece here that we'd like to be able to do something with, because if we could bound that, then the rest of it we already know that converges. So here is what we're going to do. We're going to let big N be a natural number, and big N is going to be greater than, and we'll come to see later why this is what I'm picking. 1 over 1 minus x minus c over y minus c. Now, since x minus c is less than y minus c, this thing we're subtracting off is less than 1, so by the Archimedean property, n exists. And then if little n is bigger than, greater than, or equal to big N, I think I will skip some algebra here. Then what we end up with discovering is that n minus 1 over n is bigger than x minus c over y minus c. You can do this with a little bit of algebra. Then let's consider this quantity, the things we're trying to deal with. I'm going to replace all the n's by n minus 1s. So we get x minus c to the n minus 2, y minus c to the n minus 1, and then we have to multiply that by n over n minus 1 times x minus c over y minus c. But then we can see that this piece is in fact less than 1. So this is less than n minus 1 times x minus c over y minus c to the n minus 1 and then to the n minus 2. So this sequence, the sequence of n x minus c to the n minus 1, y minus c to the n, if we start at big N, this is decreasing. So if m is any natural number, m is at least 1, then m times x minus c to the m minus 1, y minus c to the m, that's less than or equal to the maximum of that quantity. For m between 1 and capital N. Up to capital N, we're not quite sure what's going on, but after capital N, that's a decreasing thing. So the biggest it can be is the biggest it gets in here, and since there's finitely many of these things, if we call this thing capital, if we name this maximum capital M, we see that that is finite. Now we observe that this sum converges. So by the comparison test, so does this thing. Because remember, you can write it this way. Y minus c to the n times the thing we have just at great length shown as bounded less than our big M. So this thing converges. So we've seen that our series converges is absolutely whenever x minus c is less than r. So we have that p is less than or equal to r. Sorry, greater than or equal to r. And that completes the proof. Now let's talk about derivatives of power series. Your book does this as one big theorem, but I'm going to break it up a little bit. So let's start with a power series with radius of convergence let's name the radius of convergence r, and let's assume that the radius of convergence is positive. And what can we do? We're going to define a function f that goes from this interval c minus r up to c plus r, open interval to the real numbers, by f of x is our sum. And then f is differentiable and also continuous. Differentiable implies continuous, but let's write it explicitly. And also, I can write down a power series for the derivative, and it's exactly the power series you think it ought to be. So power series, if they have positive radius of convergence, everywhere inside the radius of convergence, they're continuous and differentiable, and their derivative also is a power series. The proof is not hard. The proof involves a lot of the stuff we did in section 4.1. One of the big reasons why sections 4.1 and 4.2 are put together is because of what we're going to do. Let's let g of x be our thing that we're claiming is the derivative. And by the previous proposition, this series also has radius of convergence g. R, I mean. So that means that G is well defined from C minus R to C plus R. That is, g of x exists for every x in that little interval. And now we let f sub n be the partial sum stopping at big N. Then Fn prime is the partial sum of the series for G. All right, so then we're going to use theorem 4.2.4c. This is the theorem that says that power series not only do they converge absolutely. Then Fn prime, it's a partial sum of the power series for G, so Fn prime converges uniformly to G on this little interval. And we do know something about uniform convergence of derivatives. And we've also got that Fn converges uniformly to F on the same interval. So by proposition 4.1.10, f prime is g. If your derivatives converge uniformly and your function converges at one point, which is certainly true since we've got uniform convergence, then the limit of the derivative is the limit of the derivative. The derivative of the limit is the limit of the derivatives. And this is true for all of possible little r. All positive little r that are less than big R. So we must have that f prime equals g on the open interval, but with the big R's as well. And so the function given by the power series is differentiable and has the right derivative in the region we care about. And then you can use proposition in 2.2.4 to see that if f is differentiable, it must be continuous, or you can use theorem 4.1.6. The fn's, the partial sums are polynomials, so they're continuous, and you've got uniform convergence by theorem 4.2.4c, which means you've got continuity by theorem 4.1.6. We've got f is continuous. And that completes the proof. But our power series for the derivative has the same radius of convergence. So we could do this again. We could show that the derivative has a derivative. And we could show that the derivative of the derivative, that's going to be another power series with the same radius of convergence. So we can establish that power series, they don't have just one derivative, they have infinitely many continuous derivatives. And it's a pretty simple inductive argument to go from the proposition we've just proven. So let's go ahead and write that out. So here is the proposition we have just proven. Here is the theorem as it is stated in your book. If you've got a power series, with positive radius of convergence, and let's let f be the function defined. Is the function that your power series converges to. Then we've got the following things are true. So I'm going to put this in a slightly different order as in your book. So this is what Conway calls part B. If k is greater than or equal to 0, then this power series, n factorial over n minus k factorial, then you put an x minus c to the n minus k, has the same radius of convergence. And then part A, it says that f has k derivatives, and the kth derivative is equal to the sum of the power series. And then part C is that the kth derivative of f at the point C is equal to k factorial times a sub k. And the proof is just an induction argument applied to the proposition we just did. That is, the proof of part B is two propositions ago. Part A is one proposition ago, and then you just use induction to prove this for all k. And then part C is you just plug in C for x in part A. So the last topic in this section is the following question. So we've seen that if you start with a power series with positive radius of convergence, that gives you an infinitely differentiable function. Can you go the other way? If you start with an infinitely differentiable function, do you necessarily have a power series? So let's say you've got a function that's smooth. That means it's got infinitely many continuous derivatives on some open interval. And all power series have infinitely many continuous derivatives, so this is certainly a necessary condition for having a power series. So the question is, when does... let's let C be a point in AB. When is it the case that f of x it can be written as a power series? Well, power series only really can make sense in intervals around C. So when are there some coefficients and some positive radius of convergence such that f of x equals this power series? And I'll point out from our theorem, let's notice, you know what an is. It's got to be n derivatives of f at c over n factorial. Now, this isn't always true. There are some smooth functions that don't have power series. You'll look at an example like this on the homework. But here is a theorem. Let's let f be smooth on some interval. And let's let C be a point in this interval. And let's suppose that there is a positive real number m such that if you take the supremum over all points in your interval, and you also take the supremum over all non-negative integers k, then f to the k of x over m to the k. So it's okay if your derivatives grow. It's even okay if your derivatives grow like a power. Let's suppose this is finite. Then the conclusion is that is equal to f of x is equal to its power series. For all x in the interval. And the radius of convergence is big enough to cover the whole interval, is at least and the proof is just Taylor's theorem. So if x is in our interval, unless it's the point C, but everything obviously works at the point C, then f of x minus a partial sum that is going to be equal to, by Taylor's theorem, there's some other point in the interval y such that this is true, and then we can put our upper bound C, this supremum here, we're taking that to be equal to C. And then we can put an m to the k plus 1, x minus c to the k plus 1, all over k plus 1 factorial. And you can show using various things you want. This approaches 0. As big as k. So, let's make it a partial sum from n equals 0 to k as k goes to infinity. That's not too hard to prove. You can, for example, use the ratio test to show that the sum of these things converges, and so they must be going to 0 pointwise, and then we see that we're converging at every point in the interval from A to C, so the radius of convergence must be the biggest x gets from C in that interval.